A credit card cannot slip between stones cut thousands of years ago. How did ancient engineers achieve that flawless precision without any modern tools? By the end of this journey, you will possess a new framework for seeing every ancient monument not as a mystery, but as a masterpiece of practical intelligence. We will uncover how master builders turned simple ropes and water into precision instruments, and why a perfect stone joint was about far more than just strength. What forgotten human skill do you believe is most impressive? The obsession with a credit card gap misses the entire point of their achievement. For an ancient master builder, precision was never a sterile number on a screen. It was a living idea defined by three inseparable principles. First, functional perfection. The stone must fit so well it transfers weight perfectly and lasts for ages. Second, structural integrity. The entire wall or pyramid must stand unshaken by time or tremor. And third, often overlooked, symbolic alignment. The placement had to resonate with celestial patterns or sacred geometry, making the structure right in the eyes of both the community and the cosmos. Their standard was not the micrometer, but the human hand, the trained eye, and the plumb line. This was a tactile world where a craftsman learned the language of stone by feeling its grain, hearing the ring of a well-struck chisel, and judging a surface by the way light spilled across it. We must abandon the notion that their technology was primitive. It was simply different, a sophisticated paradigm built on a deep, intuitive partnership between the maker and the material. A master stonemason did not just cut rock, he understood it, his lifetime of experience woven into his very senses. To solve the mystery of how they built, we must first understand how they saw. And they saw a world philosophy of working with the grain of the universe, not against it. The result was more than just structural soundness. It was a deep, almost spiritual harmony between the creation and its setting. The monument felt as if it had grown from the earth, rather than being placed upon it. This reverence for natural templates hints at a truth we often overlook. Their greatest tool was not made of metal or rope, but of patient, attentive perception. But observation alone could not raise a pyramid. To translate that natural harmony into a towering, ordered structure required a second principle, the creation of a universal language of measurement. In a world without factories, consistency had to spring from the one thing every builder carried with them, the human body itself. This was the birth of units like the Egyptian cubit, the length from a man's elbow to the tip of his middle finger, along with its subdivisions, the palm and the digit. These were not rough estimates, they were meticulously standardized, often linked to the physical proportions of the reigning pharaoh. His forearm became, by decree, the official cubit for the kingdom, a brilliant political and practical move that centralized control over every major construction project. Archaeologists have found exquisite cubit rods of wood and stone, the ancient equivalent of our certified tape measures, etched with precise divisions. These rods were the master copies, ensuring that a cubit measured in the quarries of Aswan was exactly the same as a cubit used to align the inner chambers of a temple in Thebes, hundreds of miles away. This system was a stroke of genius in its accessibility. Every worker, regardless of literacy, understood the measure intuitively. He could literally feel the standard in his own limbs. A foreman could call for a block to be cut to 10 cubits, and the team knew that length viscerally as 10 stretches of a forearm. It transformed abstract geometry into a shared bodily knowledge. The rhythm of construction became a collective dance guided by this common pulse. This human scale measurement did more than ensure blocks fit together. It wove the monument itself into the fabric of the society that built it. The very proportions of their greatest temples and tombs were expressions of a scale derived from their own ruler, literally embedding their cultural identity into the stone. It was a system both profoundly personal and perfectly scalable, turning individual effort into a symphony of coordinated precision. Yet a standardized ruler is only useful if you can draw a straight line or a perfect right angle across a vast construction site. This brings us to the third principle, the ingenious mastery of simple geometry and proportional systems. For these ancient engineers, complex precision was not achieved with complex machines, but with the elegant application of fundamental truths that had been understood for. Their most powerful tools were often nothing more than stakes and rope, but in their hands, this humble cord became a precision instrument of breathtaking capability. Take the simple act of creating a perfect circle, a shape fundamental to everything from stone columns to celestial observatories. By driving a central stake, tying a rope to it, and walking the rope's end in a path while keeping it taut, a worker could scribe a flawless circle of any desired radius onto the ground. This was the original compass, a tool of infinite scalability. The same principle, in reverse, could verify the roundness of a massive column drum by checking if the distance from its center to its edge was constant. But their geometric genius shone in establishing the most crucial angle of all, the perfect 90-degree corner. The integrity of every rectangular structure, from a humble house to a mighty pyramid, depended on it. Their solution was the timeless 3-4-5 triangle. A team would lay out a rope with 12 evenly spaced knots, creating segments of 3 units, 4 units, and 5 units. By staking the rope so that the 3-unit and 4-unit sides met at a corner, and then pulling the 5-unit section taut between the ends, they forced the angle between the 3 and 4 sides to be a perfect right angle. This method, requiring no modern instruments, could be scaled up immensely, allowing them to square the corners of foundations covering acres with an accuracy that still astounds surveyors today. This geometric literacy was far more than practical carpentry. It was a form of sacred knowledge. The same mathematical ratios that ensured a wall would stand straight were believed to reflect the harmonious order of the cosmos. The proportions of a temple were often based on these perfect geometric shapes, circles, squares, and triangles, linking the earthly construction to celestial principles. This spiritual dimension provided a powerful motivation for its meticulous application. A mistake in a right angle was not just a structural flaw, it was a spiritual misalignment. The geometry was their unshakable software, a set of rules that translated divine perfection into terrestrial form. When you look at the stark, precise lines of a massive stone platform, you are not just seeing cut rock, you are seeing a prayer made manifest through rope, stakes, and unwavering belief in a mathematical truth. This fusion of the pragmatic and the profound is what elevated their craft from mere construction to a legacy in stone. That universal language of measurement and geometry was the master plan, but the first physical word was written in the quarry. This raw, rugged landscape was not merely a source of stone, it was a vast library of potential, and the master builders were its most discerning readers. They understood that true precision could not be carved into a flawed block, it had to be born from one. Their process began with an act of profound geological discernment. Teams of experienced scouts would survey entire cliff faces and rock beds, searching not just for quantity, but for perfect quality. They sought out specific sedimentary layers known for their uniform grain, consistency in color, and most importantly, a complete absence of hidden fissures or weak inclusions. A single hidden crack could doom a 20-ton block to shatter during transport or, worse, fail centuries later within a sacred wall. This selective harvesting was their primary and most effective form of quality control, a decision made with hammers that rang clear and eyes that could read a stone's history in its striations. Once the perfect stratum was identified, the real artistry of extraction began. Instead of brutally attacking the rock, they collaborated with its inherent structure. They would meticulously trace natural horizontal weaknesses, known as bedding planes, using nothing more than chisels and mallets to define a clean separation line. To free the block vertically from the living mountain, they employed a technique of elegant force. Workers would drill a series of closely spaced holes along the desired fracture line. Into these holes they drove dry wooden wedges. Then, with careful ritual, they would pour water over the wedges. The wood would swell with tremendous, inexorable pressure, and the rock, stressed along the precise line they had dictated, would groan and crack with a clean, straight fracture. It was a method of incredible finesse, using the natural properties of wood and water to persuade the stone to release itself. The result was a rough block whose faces were already remarkably flat and square, a monumental head start. This quarry-born precision meant the stone arrived at the construction site not as a chaotic mountain fragment, but as a dignified raw material, already whispering the shape of its final purpose. The deafening, dusty chaos of the quarry was, in truth, a place of silent, calculated intention, where the journey of a perfect joint truly began. A block fresh from the quarry was a promise, not yet a finished word in the monument's story. To fulfill that promise, ancient craftsmen turned to a surprisingly minimalist toolkit, one where brute force and delicate finesse were two sides of the same chisel. They did not have hardened steel, but they had something perhaps more valuable, a deep understanding of how different materials interact. For the initial shaping, they used heavy stone hammers, often made of a tougher rock like dolerite, to knock off major protrusions. For finer work, they employed copper chisels. While softer than the granite they often cut, these chisels had a secret. They were constantly resharpened and, more importantly, used with a precise, percussive technique that fractured the stone's crystalline structure along controlled lines. It was a dialogue of impacts, each blow strategically placed to guide the rock toward its intended form. This stage was called dressing, and it was a patient, rhythmic art. The mason would shift from the heavy hammer to a lighter pounding stone, pecking away at the surface in a controlled pattern that gradually reduced the stone to within a finger's width of its final dimensions. The sound of this work was not a chaotic cacophony, but a kind of stony music, the pitch and ring telling the craftsman about the integrity of the material beneath his tools. Yet even the most careful pecking left a rough, pitted surface. To achieve the legendary smoothness, they entered a new phase of quiet abrasion. Using a simple slurry of wet sand, often a harder quartz sand, they would grind the surface with a flat stone back and forth for hours, then days. The quartz crystals acted as countless microscopic cutting teeth, slowly, inexorably wearing the granite or limestone down to a plane as flat as still water. This process alone could bring two stones very close together. But for that final, breathless fit, the ancient engineers employed a method of sublime simplicity, one that required no measurement at all, only patience and physical intimacy. They would take two destined stone faces and place them together, but with a layer of abrasive slurry between them. Then, they would slide one stone over the other, again and again, sometimes for weeks. This technique, known as dry stone polishing, was the ultimate act of collaborative precision. With each pass, the high points on each stone were ground down by the abrasive. Over time, the two surfaces did not just become flat, they became perfect negatives of each other, a unique mating pair. Any microscopic hill on one stone would create a corresponding valley on its partner. The joint was not made to an abstract external standard, but was born from the direct, prolonged conversation between the two blocks themselves. When they finally locked together for the last time, the abrasive washed away. The fit was so complete that friction alone could often hold them, even without mortar. This was not assembly, it was a form of stone marriage, a bond created through shared experience, resulting in a seam that was less a gap and more a continuation of the same solid mass. The credit card test is passed not because they measured to 1/1000th of an inch, but because they allowed the stones to find their own perfect union through the slow, faithful grammar of friction. The true test of a perfect stone began the moment it left the quarry floor. A 20-ton block of granite, its surfaces now whispering smooth, presented a paradox. It was a masterpiece of precision, yet utterly helpless. It could not roll, it could not walk, and placing it on a wheel would have crushed any known axle of the ancient world. Moving these megaliths across miles of rugged terrain was not a separate challenge from building. It was the first and most dramatic act of construction, a slow-motion ballet of brute force and exquisite control. The solution was never a single secret machine, but a symphony of simple physics and staggering human coordination. For the foundational journey, engineers prepared a sacred highway, a causeway. These were not mere dirt paths, but engineered roadways, often lined with timber or smoothed stone. Upon this prepared track, the block would be mounted on a massive wooden sledge. But dragging a sledge carrying such immense weight creates catastrophic friction, enough to grind the runners into the earth and halt everything. Here, the ancient engineers employed a moment of liquid genius. Archaeological evidence from sites like the Egyptian pyramid causeways shows traces of a slick substance, often a slurry of water and clay. As the team pulled, laborers stationed at the front would pour this lubricant onto the path just ahead of the runners. The sledge would glide forward on a temporary film of mud, reducing friction by as much as half. It was a continuous, moving miracle, turning the earth itself into a fleeting, slippery ally. But what of the truly monstrous stones, those 50 or 100-ton colossi that seemed to defy all logic? For these, researchers believe a more dynamic technique may have been used, one akin to walking the giant to its destination. Imagine fitting the stone block into a stout wooden cradle. Using levers, teams could rock the block forward onto one curved edge of the cradle, then swing it to the other side, advancing it a few inches with each rhythmic tilt. This rocking and rolling motion, a controlled, incremental stumble, could navigate uneven ground where a straight drag was impossible. The real engine, however, was not wood or water, but human will. We picture hundreds of laborers straining on ropes, and that is correct, but it was not chaotic pulling. This was orchestrated force. A master overseer, likely using drumbeats or rhythmic chanting, would set the pace. Each pull would happen on a unified beat, turning individual effort into a single, massive pulse of power. This coordination was critical not just for movement, but for preserving the stone's precious prepared surfaces. A sudden jerk or uneven pull could chip a corner, mar a face, and ruin months of meticulous dressing. The transport was a precision task of its own, a careful, kilometer-long negotiation where the prize was delivering perfection intact. The journey transformed the stone. By the time it arrived at the sacred site, it was no longer just a piece of the mountain. It was a veteran of an epic pilgrimage, tested and ready to take its ordained place for eternity. The final, breathless act was not the movement, but the placement. Arriving at the base of a soaring pyramid or a towering temple wall, the perfectly dressed stone now faced its ultimate trial, gravity. To lift a 20-ton block 10 stories high with nothing but human muscle seems like a task for giants. Yet the ancient engineers had already solved this vertical puzzle, not with magic, but with a profound understanding of leverage and gradient. Their secret was not a single invention, but the masterful orchestration of simple machines, tools that transformed overwhelming force into manageable, precise control. The most fundamental of these was the lever, a principle as old as the first branch used to move a rock, but in their hands it became an instrument of surgical placement. Imagine a massive timber, its end carefully wedged under a stone block resting on a temporary platform. On the long opposite end, a small team of workers would apply downward pressure. The levers lengthened their strength exponentially, allowing them to lift one edge of the colossal weight just enough to slip a wooden shim or a round log underneath. By repeating this process, alternating levers at each corner, they could walk the stone upward, inch by controlled inch, onto a higher tier. This was not a violent hoist, but a careful, ratcheting ascent, preserving the stone's fragile edges and maintaining its alignment. For the grand, sweeping ascent up the side of a pyramid, they employed the inclined plane, perhaps their most visually humble yet conceptually brilliant tool. Archaeologists believe workers constructed massive ramps of packed earth, brick, and rubble, spiraling or straight, that grew alongside the monument itself. These ramps turned an impossible vertical lift into a long, gradual, horizontal pull. Teams dragging a sledge up a gentle slope experience only a fraction of the weight they would need to lift directly. As the pyramid grew taller, the ramp was extended longer and higher, a temporary mountain built to create a permanent one. The true genius, however, lay in the combination. Levers were used to guide the sledge and make fine adjustments at each stage of the climb. Workers might lay wooden rollers on the ramp's surface to reduce friction further. It was a symphony of simple physics, each element playing its part. The inclined plane conquered the height, the lever provided the finesse, and the lubricated sledge delivered the load. This step-by-step procedure demystified the monumental. It broke an awe-inspiring, seemingly superhuman, task down into a repeatable sequence of logical, physical actions that a coordinated team could execute day after day, block after block. They did not overpower the stone, they outthought its weight, using the immutable laws of the natural world as their silent, steadfast partners. The ramp and the lever were not just construction equipment, they were the very scaffolding of their ambition, allowing human intention to rise, patiently and irresistibly, against the pull of the earth. But a perfectly placed stone is meaningless if the entire foundation beneath it is askew. Before the first cornerstone could be laid, before the grand alignment with the stars could be locked into place, the ancient engineers had to perform their most sacred and critical act: establishing a perfect earthly grid. This was the moment where intention met the unyielding ground, where the dream of a monument that would touch the heavens had to begin with a plane as flat and true as the surface of a still pond. Their first challenge was defeating the curve of the earth itself, creating a level foundation over distances that the human eye could not possibly judge. Their tool for this was both humble and brilliant, a simple trench filled with water. Across the sprawling site, workers would dig a network of shallow channels, connecting them to form a continuous liquid ring. They then filled this trench with water and waited. The surface of still water, by its very nature, seeks a perfect horizontal plane, a line perpendicular to the pull of gravity. By measuring down from this liquid horizon at thousands of points across the site, teams could drive marker pegs into the earth, each peg's top precisely the same distance below the water's surface. When the water was drained, what remained was a forest of tiny stakes, all defining one unbroken, level plane across acres of uneven land. This was their master datum, the non-negotiable baseline from which all height would be measured. Every stone, from the deepest foundation block to the apex capstone, would ultimately refer back to this calm, temporary sea they had conjured from the dirt. With a true level established, they then turned their gaze upward to solve the second part of the grid, cardinal alignment. A temple meant to face the rising sun on the equinox could not be off by even a single degree, as the error would magnify over its immense length. For this, they became astronomers. One prevalent method used a simple sighting tool, two vertical rods placed a long distance apart on an east-west line. By observing the sun's shadow or the rising point of a key star over successive mornings, they could adjust the rods until the celestial event lined up perfectly between them. This invisible line in the sand, this axis born from watching the sky, became the monument's spiritual and geometric spine. Another method used the gnomon, a single vertical pole. By tracing the arc of its shadow throughout the day and marking the shadow's shortest length, which points true north-south, they could again derive their sacred directions. This foundational work was not merely technical, it was ceremonial. The act of setting the grid was the act of marrying earth to sky, of fixing a fleeting celestial event into permanent stone. A mistake here would be catastrophic, not just a structural wobble, but a spiritual dissonance that would echo in every subsequent layer. The water in the trench and the shadow of the pole were their most sophisticated instruments, translating the cosmic order into a language of stakes and string that every worker could understand. Once this grid was immutable, the real building could begin, secure in the knowledge that every block that followed was not just stacking upward, but building outward from a perfect fragment of the universe itself. With the cosmic grid set and the stones patiently waiting, the final act of precision was not a dramatic hoist into place, but a quiet, meticulous conversation between the blocks themselves. This was the masterful craft of trial and error dry assembly. Before any block made its permanent, gravity-locked descent up the ramp, many ancient cultures would first stage a full rehearsal. In a flat, open area near the construction site, they would temporarily fit the stones together without any mortar, building entire sections of a wall or even a vaulted chamber on the ground. This was not a rough approximation. It was a full-scale, three-dimensional proof of concept. The goal was to turn the construction site into a giant calibration workshop, where the stones themselves became the ultimate measuring instruments. Each block was carefully lowered against its neighbor, and the craftsmen would then read the joint with their hands and eyes, feeling for the slightest resistance, searching for any telltale gap where light could spill through. A high spot, a tiny proud bump on one stone preventing perfect contact, would be meticulously marked with a dash of or charcoal. The block would then be separated, and the marked area patiently ground down with abrasive slurry, a process of subtraction measured in grains of sand. Then, the stones would be brought together again, and the process repeated. This created an iterative feedback loop, a slow, methodical dialogue between intention and material. It was a system that prioritized ultimate, flawless fit over raw speed. Think of it as solving a monumental stone puzzle, but where you could gently reshape each piece until it slid into its neighbor with a hushed, satisfying finality. This dry assembly solved problems that no plan or measurement could foresee. It revealed how an entire course of stones would settle under its own weight. It allowed them to check the alignment of dowel holes for metal cramps that would later lock blocks together, and it ensured that the final permanent assembly high on the temple wall would lock together seamlessly, transferring weight perfectly across every surface. The time spent in this earthly rehearsal was an investment in eternity. It transformed the terrifying finality of placing a 50-ton block 100 feet in the air from a leap of faith into a guaranteed outcome. When that block was finally winched into position for real, the builders knew with absolute certainty that it would greet its waiting partner not as a stranger, but as an old friend. Its contours already memorized and perfected in the calm of the workshop below. This dry assembly was a rehearsal for permanence, but some ancient builders took the concept of a perfect fit to an almost unbelievable extreme. They moved beyond simply stacking uniform blocks and entered the realm of the structural puzzle, creating walls where stones were not merely placed together, but were intricately carved to become inseparable parts of a single, interlocking whole. The most stunning examples of this are found not with chisels and copper, but high in the Andes at Inca sites like. Here, the stonework defies simple explanation. Enormous blocks, some weighing over 100 tons, are fitted together with a breathtaking complexity. Each stone is a unique polygon, boasting anywhere from 12 to 30 or more meticulously carved faces and angles. These are not flat surfaces, they are three-dimensional keys, and each neighboring stone is the corresponding lock. When placed, they mesh together with a precision so tight that the famous credit card test seems trivial. The joints are so complex and seamless that in many places not even a blade of grass can find purchase. This is architecture as a giant, eternal jigsaw puzzle, but one carved from solid granite. The engineering genius here is profound. This polygonal masonry created walls of incredible seismic resilience. When an earthquake strikes, sending shuddering waves through the ground, a rigid wall of rectangular blocks is vulnerable. It can crack and topple as a unit, but a wall of interlocking polygons behaves differently. The complex, zigzagging joints and the myriad of contact faces allow the stones to shift and settle minutely against one another, dissipating the earthquake's energy through friction and subtle movement, before settling back into a stable configuration. The wall flexes like a living thing, then returns to stillness. To achieve this, the builders employed a mindset we might call reverse engineering in stone. There was no standard block to mass produce. Instead, the process began with placing a first, foundational stone. The masons would then carefully shape the next stone to fit perfectly against the unique contours of the first. Once that second stone was set, the empty space waiting for the third stone was now defined by the two unique faces beside it. Each new block was custom carved on-site to solve the specific, evolving spatial puzzle created by the stones already in place. The blueprint for never existed on parchment or clay tablet. It resided entirely in the spatial memory and visionary planning of the master mason. He had to hold the entire, sprawling design in his mind, foreseeing how each uniquely shaped block would contribute to the overall stability and form of the wall, sometimes courses ahead. This required an extraordinary form of intelligence, a fluid, three-dimensional reasoning that could translate a mental model into a mountain of granite, one perfect, perplexing piece at a time. It stands as a testament not just to patience, but to a different way of thinking about stone, not as inert material to be dominated, but as a dynamic partner in a silent, monumental conversation. That three-dimensional stone puzzle, however, was a masterpiece of the unique. For the rhythmic, repeating elements that gave ancient architecture its majestic scale, a different kind of genius was required. When a temple demanded 40 identical columns, each composed of 10 perfectly matched drums, the solution could not rely on a single master mason's memory. It demanded a system that could replicate perfection again and again. This was the birth of the seventh principle, the physical template, an innovation that quietly ushered in a revolution of consistency. For elements like column profiles, decorative moldings, or the complex curves of a capital, ancient workshops likely employed master patterns. These templates were the DNA of the design, carved once in fine detail from a durable material like wood, slate, or even bronze. A master sculptor would pour his skill into creating this one perfect prototype, capturing every subtle swell and shadow of the intended form. This prototype then became the factory's heartbeat. To produce a column drum, workers would first rough out a cylinder of stone. Then, the template would be applied. Imagine a wooden board cut into the exact negative profile of the desired column's curve. A craftsman would press this template against the spinning or stationary stone block, using it as a guide to check his work. He would carve away any material that protruded past the template's edge, slowly revealing the identical shape, locked into the wood's memory within the new stone. This simple act transformed artistry into a reproducible process. It meant that a work gang in a quarry 10 miles away, using an identical copy of the master template, could produce a column drum that would fit seamlessly with one made at the main temple site. This was early mass production, a concept we associate with the industrial age, but which found a profound expression in the ancient world. It guaranteed not just visual harmony, but structural predictability. Every dowel hole could be drilled in the same location, every lifting boss carved in the same spot, because the template dictated it. This system of standardized, interchangeable parts allowed for staggering logistical feats. Construction could be decentralized, with multiple teams working simultaneously on different components across a kingdom, all converging at the sacred site with the confidence that everything would lock together. The template democratized precision, allowing skilled but not necessarily visionary craftsmen to contribute to a grand, unified vision. It turned the act of creation into a chorus, where every voice sang the same, perfect note, ensuring that the final temple rose not as a collection of similar parts, but as a single, coherent thought. Repeated in stone until it became a mountain of order, for these builders, a perfect right angle was more than a construction necessity, it was a sacred echo. The precision we marvel at today was never just about engineering, it served a deeper, celestial purpose. Every temple, every pyramid, was a bridge between the earth and the sky, and its construction began not with a foundation trench, but with generations of patient stargazing. To align a monument to the rising sun on the summer solstice, or to the pole star, required a profound, long-term partnership with the cosmos. Ancient astronomers, often the priest engineers themselves, would observe the slow dance of the heavens for decades, marking the sun's furthest travels north and south, or charting the unwavering point around which the night sky turned. This accumulated wisdom was then translated, with breathtaking ingenuity, from celestial motion into terrestrial measurement. A simple pair of aligned stones, called a backsight and foresight, could capture the precise angle of a star's rise. A long, leveled courtyard became a giant observatory, where the shadow of a distant mountain peak would touch a specific marker only on one sacred day each year. This was not guesswork, it was a science of alignment, turning the entire landscape into a permanent calendar and compass. The spiritual imperative behind this precision cannot be overstated. A temple aligned to the solstice sun did not just mark a date, it participated in a cosmic event. It captured the first light of the reborn sun, flooding an inner sanctuary with a beam of gold on the darkest day of the year, a tangible symbol of divine favor and cosmic order restored. This ritual alignment made the structure itself an active participant in the cycles of nature and the will of the gods. A mistake of a single degree would mean the sunbeam missed its target, the ritual failed, and the harmony between the people and the universe was broken. This religious imperative fueled a level of care that went far beyond mere utility. It transformed the mason's chisel into an instrument of devotion, and the surveyor's line into a prayer made visible. The drive for perfection was by a profound belief that they were building a permanent home for the divine, a machine for connecting humanity to the forces that govern life itself. This spiritual dimension provided the relentless patience, the willingness to grind a stone for months, to move a block an inch at a time, because the consequence of error was not just structural, it was cosmic. The monument had to be right in every sense of the word. And so, the same hands that laid a perfectly level foundation also encoded the heavens into its plan, ensuring the work of man would forever resonate with the music of the spheres. The celestial alignment of a temple was a secret held in the stars, but the art of building it was a secret held in human hands. This brings us to the eighth and perhaps most vital principle, the transmission of knowledge through apprenticeship and guilds. In a world without engineering textbooks or digital blueprints, the entire library of precision stonework lived within the minds and muscle memory of living craftsmen. The master builder was not just an architect. He was a walking repository of centuries of accumulated wisdom, a direct link in an unbroken chain of experience. The primary school for this knowledge was the master-apprentice relationship, a bond that went far beyond simple instruction. A young boy, often from a family of masons, would enter a master's workshop as a child. His first years were spent not carving stone, but in humble service, mixing mortar, fetching water, and simply observing. He learned by immersion, absorbing the rhythms of the workshop, the sounds of different tools on different stones, and the unspoken language between craftsmen. Slowly, under the master's watchful eye, he would graduate to holding a chisel, then to rough shaping, then to the finer arts of dressing and polishing. This was knowledge passed through the body, not the page. A master would place his hands over the apprentices to demonstrate the exact angle and pressure for a specific cut, a technique impossible to describe in words. He would share tricks of the trade, like which quarry sand made the best abrasive slurry, or how to spot a hidden flaw in a block by the sound of a tap. These were the trade secrets, guarded not out of selfishness, but because they represented a lineage's hard-won reputation. This system naturally evolved into formal guilds or powerful family lineages. In many cultures, stonemasonry became a hereditary craft, with fathers teaching sons, uncles teaching nephews, ensuring that the specialized knowledge stayed within a trusted circle. These guilds acted as both unions and universities, controlling quality, setting standards, and protecting the economic value of their members' rare skills. They became living libraries, where the collective memory of generations was preserved through ritual, story, and relentless practice. The oral tradition was crucial. Complex rules, like the proportions for the 3-4-5 triangle or the formulas for calculating volumes, were encoded in chants, poems, or mnemonic devices, making them easy to remember and pass on. This practical, person-to-person transmission had a profound advantage. It was self-correcting and adaptive. If an apprentice discovered a slightly better way to shape a dovetail joint, that innovation could be incorporated into the living tradition and passed to the next generation. The knowledge was not frozen in a manuscript. It was a river, constantly refined by the flow of experience. This explains how a standard of precision could be maintained for 1,000 years, even across the rise and fall of dynasties. The library never burned down because it was not made of papyrus, it was made of people. When we look at a wall of perfectly fitted stones, we are not just looking at rock, we are witnessing the silent, accumulated genius of countless unnamed masters and their devoted apprentices. A legacy built one carefully guided hand at a time. The legacy of that living knowledge is etched most famously into the desert horizon. For a vivid demonstration of ancient precision, we need look no further than the Great Pyramid's lost skin. Before it was the stepped mountain we see today, it was something far more astonishing. The entire structure was originally sheathed in highly polished, bright white limestone. These casing stones were not merely decorative slabs, they were a masterpiece of applied geometry. Each block was a trapezoid, its inner face rough to bond with the core masonry, but its outer face and sides were cut with an accuracy that still defies easy explanation. When assembled, these thousands of individual faces created a single, sweeping plane for each of the pyramid's four sides. A surface so flawlessly flat and so brilliantly reflective that it would have gleamed like a faceted jewel under the Egyptian sun. The question of how this perfect plane was achieved leads us to one of the most compelling theories in ancient engineering. While the grand ramps used for lifting blocks are well discussed, some researchers propose these ramps may have served a dual, more subtle purpose. Imagine the final phase of construction, with the pyramid's core complete and the summit capped. Workers would now begin the painstaking process of applying the casing stones from the top down, smoothing the rough core into a perfect geometric form. A massive, temporary ramp of earth and brick, still encasing the structure, would have provided more than just access. Its inward-facing slope could have been carefully shaped and leveled to act as a giant, continuous reference surface. As masons set each casing block, they could check its outward face against this prepared earthen template. Using simple plumb lines and taut cords stretched from the ramp's surface, they could ensure every single stone was aligned to the same exact angle, creating that seamless plane. The ramp itself became the master guide, a negative mold that guaranteed the final, positive form. This theory transforms the ramp from a simple lifting device into an integral part of the surveying and finishing process. It provided a constant, physical standard against which every casing stone could be measured and adjusted before the ramp was eventually dismantled, revealing the perfect pyramid beneath. The tragic loss of almost all these casing stones over centuries offers us a profound lesson. The stark contrast between the exposed, rough-hewn core blocks and the few remaining casing stones in the base is dramatic. It reveals a deliberate hierarchy of construction quality. The core was about immense strength and volume, built with robust but less finely finished blocks. The casing was about perfection, a thin, exquisite skin of unparalleled precision applied over that mighty armature. This was not a case of the entire pyramid being built to that impossible standard, but of applying that standard where it mattered most, for symbolic, aesthetic, and perhaps even reflective, celestial purposes. The smooth skin was the final word, the definitive statement of accuracy and intent, proving that for these builders precision was the glorious finish, not the hidden foundation. The Great Pyramid's gleaming skin represents the zenith of their craft, but the humble element that made it possible flowed freely from the Nile. Water was not merely a resource for these builders, it was a silent partner, a versatile tool employed with a profound and practical intelligence. We have already seen its role in creating level foundations through simple trenches, but its utility flowed far beyond that initial act. In the hands of an ancient engineer, a bucket of water became a precision instrument, a powerful lubricant, and even a temporary support system, all based on a keen, observed understanding of how liquids behave. The most straightforward application was in movement. As sledges bearing colossal stones groaned along their causeways, workers would pour water onto the path ahead of the wooden runners. This was not just to dampen dust. It created a thin, slippery layer of mud that dramatically reduced friction. The physics is elegant. The water mixes with the earth to form a fine, plastic slurry, allowing the sledge to glide rather than grind, turning an impossible drag into a manageable pull. It was a continuous, mobile miracle, harnessing fluid dynamics to defeat the immense grip of gravity and earth. But their use of water may have reached even greater sophistication. Consider the challenge of ensuring two separate foundation piers, being built dozens of yards apart, rise to exactly the same height. A simple water trench cannot link them. Some historians speculate they might have used an early form of hydrostatic leveling. Imagine two clear containers placed on the two distant points, connected by a long, flexible hose. When water is poured in, it will seek the same level in both containers, regardless of the distance or the uneven ground between them. By marking that water line on each vessel, crews working out of sight of each other could guarantee their structures were rising in perfect horizontal sync. This simple device, born from the immutable law that water finds its own level, could coordinate a sprawling construction site with flawless accuracy. There is also intriguing speculation about water's role in the daring art of arch construction. Before the keystone is set, an arch is inherently unstable, its stones wanting to collapse inward. How did they support the unfinished structure during the slow, careful placement of each wedge-shaped block? One theory suggests the use of large, water-filled leather bags. These bags could be stacked into a temporary support form that was uniquely adaptable. As the arch was built and the shape changed, workers could add or remove water from the bags, adjusting their height and firmness with a precision impossible for rigid timber scaffolding. Once the keystone was locked into place, taking the full load, the water could simply be drained away and the bags removed, leaving a clean, unsupported arch. This intelligent, fluid approach to a rigid problem showcases a mindset that saw the world not in terms of obstacles, but of available solutions. They did not just use water, they collaborated with its fundamental properties, its seeking of level, its reduction of friction, its incompressible support. Every splash and pour was an application of quiet, observed physics, turning the most common substance on Earth into the hidden key for moving mountains and raising perfect plains to the sky. The flow of water revealed the horizon, but the flow of ideas between crafts was just as vital. To understand the stonemason's mind, we must sometimes look beyond the quarry, to the glowing forges and foundries, where another ancient art achieved breathtaking precision. This was the world of the lost wax method, a metal casting technique that produced some of the most intricate bronze statues ever made. The process began with a sculptor creating a perfect, detailed model entirely from beeswax. This wax original was then carefully encased in a fireproof clay mold, with small tubes left for the wax to escape. The entire assembly was heated, and the wax would melt and drain away, leaving behind a hollow cavity within the clay, a perfect negative space that captured every subtle contour of the original model. Molten bronze was then poured into this void. Once the metal cooled and the clay mold was broken away, revealing a bronze copy of astonishing fidelity, a permanent metal echo of that first, perishable wax form. This was more than a craft, it was a philosophy of precision built on the concept of the perfect negative. The metalworker did not carve the final statue directly, he sculpted an intermediary, the wax positive, knowing it would be destroyed to create the mold that gave birth to the masterpiece. His skill lay in foreseeing the end result through the lens of its absence. This conceptual leap is where the worlds of fire and stone likely converged. A master stonemason, tasked with fitting a unique block into a polygonal wall was engaged in a remarkably similar mental exercise. He was not carving a block to an abstract ideal. He was carving it to fit the exact, unique negative space defined by the stones already in place. Just as the metalworker's mold was a custom cavity for molten bronze, the gap in the wall was a custom cavity for solid granite. Both craftsmen were thinking in reverse, solving a spatial puzzle by creating a positive form that would fill a predetermined negative. This suggests a profound cross-pollination of ideas between ancient guilds. Workshops for stone, metal, and wood likely existed in close proximity, serving the same royal or temple projects. Artisans would have shared meals, stories, and challenges. A mason struggling with a complex joint might have watched a bronze founder prepare his wax model and had a revelation. The mindset of creating a perfect fit, whether in clay for metal or in stone for stone, is a universal principle of high craftsmanship. The lost wax method proves that ancient artisans were not just technically skilled, they were sophisticated spatial thinkers. They understood form and counterform, positive and negative, and how to manipulate one to perfectly produce the other. This shared intellectual framework transcended materials. It was a language of precision spoken in wax, clay, bronze, and granite, allowing the meticulous intelligence of the founder to quietly inform the hammer and chisel of the mason, pushing the entire culture's standard of what was possible ever higher. The flawless bronze statue and the seamless stone wall were born from a pressure far greater than any workshop foreman could apply. This pursuit of perfection was not a choice, but a cultural imperative, a non-negotiable demand woven into the very fabric of their society. For the ancient master builder, the client was not a mortal king with a budget and a deadline. The client was eternity itself, and the gods were the ultimate inspectors. A pharaoh's pyramid was not a tomb in our modern sense. It was a machine for resurrection, a celestial designed to ferry his soul to the realm of the gods. A single misaligned passageway, a chamber wall that was not perfectly square, could mean the spiritual energy needed for that journey would leak away, dooming the king's eternal legacy. In the same way, a temple dedicated to a deity was believed to be the literal dwelling place of that god on earth. To offer a flawed house to a divine being was an act of profound disrespect, risking divine displeasure that could bring drought, famine, or defeat in battle. The stakes were cosmic, and therefore the standard had to be absolute. This spiritual mandate unlocked resources that seem unimaginable today. A society would willingly commit a significant portion of its wealth, its agricultural output, and the labor of thousands of its people for decades, even generations, to a single project. This was not slavery in the sense we often imagine, though it certainly involved coerced labor, but it was also a form of national service, a sacred duty that provided purpose, community, and a share in an immortal endeavor. The laborer dragging a sledge under the desert sun likely believed he was building a ramp for his god-king to ascend to the stars, and that his own place in the afterlife might be secured through this pious work. This collective belief transformed backbreaking toil into a shared pilgrimage. The political dimension was equally powerful. A mighty fortress with walls fitted so tightly that an enemy's blade could find no purchase was a statement of unassailable power. It was psychological warfare rendered in stone. A visiting ambassador from a rival kingdom, seeing the impossible precision of a royal palace's masonry, would carry home a message not just of wealth, but of a civilization possessing unknowable skills and an iron will. The monument was a permanent propaganda billboard, proclaiming the ruler's divine right and technical supremacy. This cultural engine created an environment where good enough was a dangerous failure. There was no profit motive to cut corners, only a profound incentive to invest whatever time and effort was necessary. A block could be ground for a year because the project's timeline was measured in a king's lifetime, or even across successive reigns. This long-term perspective liberated the builders from the economic pressures that define modern construction. The purpose was not merely to build, but to build forever, and to build right in the eyes of heaven and history. This is why they could employ methods that seem shockingly inefficient to us, like trial-fitting every stone on the ground before its final placement. In our world, time is money. In theirs, time was an offering to the gods, and precision was the currency of legacy. The invisible hand guiding the chisel was not that of an accountant, but of a priest, a king, and an entire culture breathing down the mason's neck, whispering that his work would stand before the judgment of eternity. Even with the immense cultural will of an empire behind them, some stones seem to defy the very laws of physics. To witness this defiance, we must travel to the valley in Lebanon, to the Roman sanctuary of Baalbek. Here, beneath the grand columns of the Temple of Jupiter, lies a foundation platform of such staggering scale that it challenges every principle we have discussed. The Romans built upon it, but the true marvel is what they built upon. 3 colossal blocks known as the form a single course in the western retaining wall. Each one is a behemoth, a limestone giant measuring roughly 64 feet long, 14 feet high, and 12 feet deep. Their weight is estimated at over 800 tons each, with a fourth, even larger block, weighing nearly 1,000 tons, left abandoned in a nearby quarry. To grasp that scale, imagine a fully loaded jumbo jet, then stack another on top of it. That is the mass of a single one of these stones. The Romans were master engineers, famous for their concrete and arches, yet that predates their most ambitious work, and its origin remains a profound mystery. The precision is as shocking as the scale. These megaliths are fitted together with joints as tight and clean as any we have seen, despite their mind-bending weight. The surfaces are flat, the corners are sharp, and they sit on a prepared course of slightly smaller, yet still gargantuan blocks. The engineering questions here are not just about how, but why. Why choose a stone of such impossible dimensions when 5 smaller ones would achieve the same structural goal? The answer may lie in that same cultural imperative for the eternal and the awe-inspiring. A wall built of stones that no enemy could possibly replicate or dismantle was the ultimate statement of power and permanence, a psychological fortress as much as a physical one. Yet, the practicalities boggle the mind. The quarry for these giants sits nearly a mile away from the temple complex, over uneven, gently sloping ground. The standard model of sledges, lubricants, and large work crews hits a theoretical wall here. The friction involved in moving an 800-ton load, even on a lubricated track, would be colossal, requiring a pulling force that exceeds what even thousands of men could generate in unison. The ground pressure might simply cause any wooden sledge to sink into the earth, no matter how well prepared the road. This has led researchers to propose more dynamic, almost unimaginable methods. Some suggest the use of enormous, purpose-built wooden wheels or rolling cages, turning the block into a gargantuan cylinder. Others theorize about a complex system of counterweighted levers, walking the stone forward in a slow, rocking pivot. The most humbling possibility is that the builders of this platform, who may have preceded the Romans by centuries, possessed a sophisticated technique for reducing effective friction or managing weight distribution that is completely lost to our historical record. The lifting challenge is equally daunting. To raise these stones over 20 feet to position them on the wall's second course defies the simple ramp-and-lever model. The temporary earth ramps needed to elevate such a mass would have been pyramids in their own right, larger in volume than the permanent structure they were meant to build. Some have hypothesized the use of immense, multiple cribbing systems, building temporary wooden towers around the block and using a coordinated army of levers to inch it upward. Like climbing a ladder one terrifying rung at a time, the abandoned 1,000-ton block in the quarry, partially detached from the bedrock, offers a frozen moment in this impossible process. It shows the same clean, precise cuts, the same ambition, but it also shows where ambition perhaps met an insurmountable logistical limit, or where the project's priorities suddenly changed. Baalbek stands as a stark and humbling monument to a possible lost chapter in engineering history. It suggests that our current reconstructions of ancient technology, while brilliant, may still be incomplete. We may be looking at the echoes of a method so specialized, so tailored to moving the unmovable, that it was never written down, only practiced on a handful of projects so grand that they were never attempted again. That does not just sit in that wall, it sits on the very boundary of our understanding, a silent challenge from the past that whispers, "You have not yet figured it all out." The stone itself dictated the terms of the conversation. Across the ancient world, a master builder's toolkit was not a fixed set of instructions, but a fluid language that changed its grammar depending on the local geology. This 11th principle, the adaptation of technique to material, reveals that their precision was never a rigid formula, but a responsive art. The methods that produced the glassy polish of Aswan granite would have been useless, even destructive, if applied to the soft, fossil-rich limestone of the Giza Plateau. Each type of stone spoke a different dialect, and the engineers had to become fluent in all of them. Granite, formed from molten rock deep within the earth, is brutally hard and densely crystalline. To work it, Egyptian craftsmen relied on relentless abrasion and the fracturing power of dolerite pounding stones. They would literally peck the surface away, grain by stubborn grain, and finish with weeks of grinding using quartz sand slurry. The process was slow and exhausting, but the reward was a surface that could resist the desert winds. Limestone, in contrast, is a sedimentary rock, softer and more uniform. Here, copper chisels could make cleaner, faster cuts. The masons could carve intricate hieroglyphs and smooth vast casing blocks with relative efficiency, but they faced a different challenge: the material's vulnerability to erosion. Their precision had to account for this softer nature, often involving protective plaster layers or specific orientations to shield vulnerable surfaces from prevailing weather. This material wisdom went far beyond Egypt. High in the Andes, the Inca worked with andesite, a volcanic stone with a tough, interlocking grain. Their astonishing polygonal masonry, with its complex, multifaceted joints, was a direct response to this material's properties and the region's intense seismic activity. The stone's inherent strength allowed them to carve those intricate, interlocking shapes, knowing the tight, zigzagging joints would flex during an earthquake instead of shattering. They developed a technique of patiently grinding stones together with abrasive sand, allowing the unique contours of each block to emerge from this prolonged, physical dialogue. In Greece, the fine-grained marble of Mount allowed for a different kind of perfection, one of slender proportions and delicate detail. The relative homogeneity of marble meant it could be split along its grain with great predictability using feathered wedges, yielding slabs that required less initial dressing. This enabled the breathtaking fluting of columns and the flowing drapery of sculpted figures, a precision of form that would have been unimaginable in coarse granite. This localization created distinct regional fingerprints of mastery. The smooth, monolithic walls of Mycenaean Greece look different from the jigsaw puzzles of, and both differ from the towering, block-and-mortar precision of Rome. Yet each style represents the highest possible accuracy achievable with its local stone, climate, and cultural needs. The engineers did not impose an external ideal. They discovered the ideal hidden within the mountain itself. They asked not, how can we force this rock to obey our universal plan, but rather, what is this rock capable of becoming, and what methods must we invent to help it reach that potential? This respectful partnership with the local earth is why ancient monuments feel so rooted, so organically part of their landscapes. The precision was not imported, it was cultivated, a specialized knowledge grown from the very ground upon which they stood. That invisible seam was never meant to be hidden. It was meant to be seen, or rather not seen, for its very absence spoke volumes. The perfectly fitted joint transcended its structural purpose to become a powerful symbol, a silent language carved in stone. In many ancient cultures, the seamless join was not merely a technical achievement. It was a philosophical statement, a physical manifestation of order triumphing over chaos. It represented the ultimate unity, where separate entities were brought together so completely that they became one, stronger than the sum of their parts. This was the builder's definitive proof of mastery, not just over stone, but over the natural world's tendency toward entropy and disorder. By creating a wall without gaps, they were demonstrating their ability to impose a perfect, human will upon the raw, unpredictable earth. The symbolism was deeply cultural. For the Inca, those mesmerizingly tight, polygonal joints were far more than an engineering solution for earthquakes. They were a profound expression of harmony. In their worldview, the earth was a living being who would sometimes tremble. A rigid wall would fight her and would break. But their interlocking stonework, with its countless angled faces, was designed to sway and settle with her movements, then lock back together. This was architecture as a gesture of respect, a way of building that said we are not conquering the land, we are dancing with it. The perfect fit was proof of that sacred accord, a structure so in tune with its environment that it could endure its tantrums. In ancient Egypt, the symbolism pointed toward eternity. A pharaoh's tomb was a machine for immortality, its integrity paramount. Any gap, any flaw in the stonework was a potential crack in the bridge to the afterlife, a weakness through which the king's Ka, his vital spirit, could escape or be corrupted. The seamless join in a pyramid's passageway or burial chamber was therefore a spiritual seal. It guaranteed the sacred geometry of the space remained pure and intact, protecting the ritual function of the monument for all time. The precision was an act of religious devotion, ensuring the stone vessel for eternity was itself eternal. This transformed the visible evidence of skill into a permanent political statement. When a ruler commissioned a temple or palace with such impossible masonry, he was not just building a functional space. He was broadcasting a message of unassailable power and divine legitimacy. A visiting ambassador would run his hand over a wall where he could not find the join, and he would understand. This kingdom commanded artisans of such skill that they could make mountains melt together. Its wealth was so vast it could afford such time-consuming perfection. Its gods were so potent they inspired such devotion in its builders. The flawless wall was a silent, intimidating diplomat, proclaiming a civilization's technical, economic, and spiritual supremacy without uttering a single word. And for the master craftsman, this was his legacy. In a world where most names were lost to time, his signature was the joint itself. That invisible line was his masterpiece, proof that his hands, his eye, and his lifetime of learned intuition had achieved something that would outlive dynasties. He may never have been named in the royal inscriptions, but for as long as his stones stood fitted, his skill was on permanent, breathtaking display. The monument was not just a testament to the king who ordered it, but to the unnamed thousands whose collective genius made the impossible stone whisper of unity, strength, and an enduring victory over chaos. That invisible joint is a signature, but it is signed with a name belonging to no single person. The flawless fit we see in a pyramid's chamber or a fortress wall was not the brilliant invention of one era, but the slow, hard-won inheritance of countless eras before it. This is the 12th principle, the quiet truth behind every masterpiece, incremental refinement over centuries of practice. These were not technologies discovered in a flash of inspiration. They were traditions painstakingly built, one project at a time, over hundreds of generations. Think of each major monument not as a finished product, but as a sprawling, open-air laboratory. A new quarrying technique might be tried on a small, provincial tomb. If it yielded better blocks with less effort, that knowledge would travel with the work gang to the next royal project. A clever method for moving stones across sand, perfected in a remote valley, could become standard procedure for a pharaoh's funerary complex decades later. Every temple foundation laid, every obelisk raised, was both an application of existing knowledge and an experiment for the future. Successes were embedded into the oral teachings of the guilds, while failures, though rarely recorded, taught equally vital lessons about the limits of stone and the strength of men. This iterative process of technological development is often invisible in the archaeological record. We see the glorious peak, the Great Pyramid, but we do not see the 70 smaller, earlier pyramids and mastaba tombs that served as its stepping stones, each one a trial run for a new angle, a new lifting method, or a new way to align to the stars. Their research and development cycle was measured not in fiscal quarters, but in the reigns of kings and the lifetimes of entire artisan families. A revolutionary idea for dressing granite, conceived by a master in the 18th dynasty, might only reach its full, breathtaking potential in a temple built by his great-grandson's apprentices. This long-term perspective changes everything. It means that what looks like a sudden, miraculous leap to us was, for them, simply the next logical step in a chain of progress stretching back further than anyone could remember. The confidence to attempt a 1,000-ton block did not come from arrogance, but from the accumulated, proven experience of moving 100-ton blocks before it. The patience to grind a surface for a year was not exceptional. It was the cultural norm, the expected pace for a craft that saw itself as a servant to eternity. This incremental refinement was the true engine behind the impossible. It allowed for the slow, sure evolution of tools, from stone hammers to copper chisels to the eventual use of iron. It permitted the gradual codification of geometry, from practical rope tricks into a sacred science. It transformed construction from a daunting task into a repeatable, scalable process, where each generation stood on the shoulders and the stonework of the last. The peak we admire is not a solitary summit, but the highest point on a vast, ancient mountain range of collective human ingenuity. Built so slowly and so surely that its builders likely never even realized they were climbing, the jigsaw puzzle walls of are not an isolated marvel of human ingenuity. This same breathtaking style of polygonal masonry, where massive, irregularly shaped stones are locked together with uncanny precision, appears in stonework separated by ocean's end. In the Peloponnese of Greece, the massive Cyclopean walls of Mycenae, built over 3,000 years ago, guard the Lion Gate with stones so large later cultures believed only mythical giants could have placed them. Across the world in the islands of Japan, the colossal stone ramparts of castles like those in Okinawa, known as walls, display the same intricate, interlocking patterns. These cultures never met, they shared no blueprints, and yet they arrived at an almost identical architectural solution. This is not evidence of a lost global civilization, but something far more profound, the independent discovery of a universal engineering logic. When faced with the same fundamental challenges, unstable ground, seismic violence, and the need for permanence without reliable mortar, human intelligence, observing the same laws of physics, can converge on the same brilliant answer. The polygonal wall is a masterpiece of emergent design, a form that naturally arises when the problem is defined by gravity, friction, and survival. In earthquake-prone regions like the Andes, Greece, and Japan, a rigid wall of uniform rectangular blocks is a death sentence. When the earth shakes, such a wall acts as a single, brittle unit, prone to cracking and catastrophic collapse along its straight, continuous mortar lines. But a wall of polygonal stones is a dynamic, flexible system. Each uniquely shaped block, with its multiple angled faces, is surrounded by neighbors on several sides. During a tremor, the stones can shift and settle minutely against one another, the complex joints dissipating the energy through countless points of friction. The wall breathes, it adjusts, and when the shaking stops, it settles back into a stable, often even stronger, configuration. It is architecture that embraces movement rather than resisting it. This convergent evolution of form speaks to a deep, observational intelligence. Builders in these disparate cultures learned, likely through trial and painful error, that nature itself builds this way. Look at a dry stone wall in a field, built by a farmer with no engineering training, and you will see smaller versions of the same polygonal fitting. It is the most stable way to stack irregular objects without glue. The ancient engineers simply scaled this intuitive understanding to a monumental level, recognizing that the principle remained true whether the stones weighed 10 pounds or 10 tons. They applied the relentless logic of physics, using simple tools to find the solution the problem demanded. The hammer and the abrasive slurry were their means, but the true architect was necessity itself, sculpting similar responses from different minds across the globe. This parallel innovation strips away the mystery and replaces it with a powerful respect for human resourcefulness. It tells us that when survival and legacy are on the line, isolated cultures can climb the same mountain of discovery by different paths and plant their flags at the same summit. The polygonal wall is not a secret code from a forgotten past. It is a brilliant, open-source answer to the Earth's oldest challenge, written in the universal language of stone. The stone's surface was a text, but its truth was not only written in light, it was sung in sound and whispered through the fingertips. For the ancient master, the most reliable instruments were not held in the hand, but were the hand itself, the ear, and a lifetime of cultivated sensation. In a world without dials or digital readouts, quality control was a deeply personal, sensory conversation between the craftsman and his material. Every strike of a tool, every pass of a palm, generated a stream of vital information. A mason shaping a granite block would periodically pause and tap its surface with a small hammer. He was not just checking his progress, he was listening. A clear, high-pitched ring sang of solid, flawless stone, its crystalline structure intact and resonant. A dull, flat thud, however, was a warning, the voice of a hidden fissure or a spongy inclusion, a fatal weakness that could cause the block to fail under pressure. This auditory diagnosis was as precise as any modern ultrasonic test, a non-destructive probe using only the physics of sound and a trained ear. The feel of the work was equally eloquent. As a craftsman drew a bronze chisel across a limestone face, the tool's behavior spoke volumes. A smooth, steady glide meant the surface was true. A sudden skip or chatter, a minute vibration traveling up the handle into his bones, signaled a proud spot, a tiny high point invisible to the eye but glaringly obvious to the touch. This tactile feedback created a continuous, real-time map of the stone's topography, guiding his next stroke without him ever needing to look away. The final test of a perfect joint was also a sensory ritual. When two prepared stones were brought together for a trial fit, the craftsman listened intently. The sound of the surfaces sliding, a quiet, gritty whisper, would change as they met. A clean, even hiss suggested full contact. Any rasping catch or uneven tone indicated a point of conflict, but the most telling sign was often the absence of sensation. Once seated, a senior mason might strike the outer face of the joined stones with a mallet. If the fit was perfect, transferring the impact seamlessly across the seam, the hammer would deliver a single, unified tone with no secondary rattle or buzz. The wall would feel and sound as one solid mass. This sensory literacy was not a vague intuition. It was a rigorous, calibrated skill, painstakingly developed over decades of apprenticeship. A master could distinguish between the ring of Aswan granite and the thud of a flawed limestone slab blindfolded. His hands could detect variations in flatness finer than the thickness of a papyrus sheet. This direct, embodied knowledge created an unbreakable feedback loop between intention and result. He wasn't following instructions from a manual, he was having a physical dialogue with the stone itself, and the stone answered him in vibrations, sounds, and resistance. We have largely outsourced this sensory judgment to machines, our ultrasonic testers and laser. They give us numbers, incredibly precise numbers. But the ancient artisan possessed a qualitative wisdom, a holistic understanding of material integrity that came from living inside the process. His ear was his oscilloscope, his palm his surface gauge, and his lifetime of accumulated feeling was the database against which every new stone was measured. This human-scale precision turned every construction site into a symphony of subtle cues, where the true blueprint for perfection was written not on parchment, but in the resonant language of solid rock. The sensory conversation with stone reached its logical conclusion in the hands of the Romans, but they changed the very language of the dialogue. Where an Inca mason might spend a month custom-fitting a single polygonal block, a Roman engineer sought to eliminate the need for such artistry altogether. Their genius was not in perfecting the unique, but in mastering the repeatable. The Roman Empire was a vast, sprawling organism, stretching from the rainy highlands of Britain to the deserts of Syria. To bind it together, they needed not just roads and armies, but a consistent, durable infrastructure that could be built quickly by local labor and to a universal standard of strength. This demand gave birth to a new engineering philosophy, one where precision was not found in the final joint, but was baked into the system from the very beginning. Their revolutionary innovation was modular design. Across the empire, brickworks and quarries produced materials to standardized sizes. A brick made in Gaul was the same dimension as a brick made in North Africa. This was a seismic shift. It meant a legion of soldiers, or a crew of local laborers, could be handed a shipment of building materials and a set of plans, and begin construction with the confidence that every piece would fit. The need for a master stonemason's lifetime of tactile skill was reduced. Precision became a property of the manufacturing process, not the assembly. The true symbol of this systematic approach was not the brick, but concrete. Roman concrete, or opus, was a technological marvel. Its precision lay not in cutting but in chemistry and engineers developed specific mix ratios for different applications, a recipe of volcanic ash, lime, and aggregate that would set even underwater. The precision was in the recipe's consistency, and in the construction of the wooden molds, that would hold the wet, plastic material until it hardened into any shape they desired. The perfect arch, the soaring dome of the Pantheon, these were not built from countless custom-cut stones. They were poured into meticulously crafted temporary shells. The craftsman's skill migrated from the chisel to the carpenter's square, ensuring the itself was geometrically flawless. This focus on systems over singular stones allowed for a staggering pace and scale of construction. An aqueduct could march across a valley not because each arch stone was perfectly dressed, but because the centering for each arch was identical. And the concrete or standardized blocks were poured or laid into that reliable template, one after another. It was engineering as replication. This modular, systematic thinking extended to everything. They developed standard plans for forts, baths, and basilicas, layouts that could be adapted to any site. A soldier transferred from one frontier to another would find a familiar fortress waiting, built with familiar materials. Roman precision was about creating a kit of parts and a set of rules so robust that they could build civilization itself, on demand, from the misty moors of England to the edge of the Sahara. It was a different kind of brilliance, one that traded the intimate, artisanal perfection of a seamless joint for the world-altering power of a reproducible, imperial system. Their legacy is not a single, breathlessly fitted wall, but the very idea that infrastructure could be systematized, scaled, and stamped across a continent, turning the chaos of conquered lands into a unified, enduring network of stone and mortar. A stretched string is the oldest straight line in the world. This simple fact is the starting point for a 14th principle, one that explores how ancient engineers transformed light and shadow into tools of precision. Beyond the plumb line and the water level, they may have harnessed the most ephemeral guides of all, visual lines and cast shadows, turning these fleeting phenomena into fixed, reliable markers for their grandest designs. The concept is elegantly direct. A length of cord, pulled taut between two stakes, creates a perfectly straight visual reference across any distance. A master surveyor, sighting along this string, could align a row of foundation stones or verify the straightness of a massive wall under construction. This was their laser level, a tool of pure tension and line of sight, requiring no technology more complex than skilled eyes and a steady hand. But their visual toolkit likely extended far beyond string. Consider the gnomon, a simple vertical rod. Its shadow, tracing a path from morning to evening, is a dynamic sundial. By carefully marking the shadow's shortest length each day, which points true north, or by noting where it fell on the equinox, builders could derive not just time but sacred direction. A notch carved into a distant stone, designed so the sun's first ray on the solstice would pierce it like an arrow of light, could lock a temple's axis to the solar year. These were not passive observations, they were active interventions, using crafted objects to capture and ritualize celestial events, translating the sun's journey into a permanent terrestrial mark. Some researchers go further, speculating about the use of reflective surfaces. A still pool of water in a darkened chamber could act as a natural mirror, projecting a spot of sunlight onto a ceiling or wall. A carefully positioned sheet of polished bronze might reflect a beam of light down a long, dark corridor to illuminate a specific point only on a significant day. These techniques would have allowed for the projection of sight lines or the marking of alignments in places where direct observation of the horizon was impossible. The underlying genius was in the standardization of the ephemeral. A shadow is different every day, but its shortest noon shadow is a constant truth. A reflected spot of light dances, but its position at a precise moment is repeatable year after year. By identifying these fixed points within nature's cycles, the engineers created a calendar and a compass from thin air and sunlight. This principle moves us from the tactile world of stone and rope into the realm of perception and projection. It suggests their mastery was not only over materials, but over the very behavior of light itself, using it to draw invisible lines of astonishing accuracy across the landscape. Guiding hands to build in harmony with the cosmos, the stretched string and the sunbeam met their match in the cold stone of the Bolivian Altiplano. At the site of Puma, part of the vast complex, lie scattered fragments of a puzzle that seems to defy the very principles we have explored. Here, precision is not expressed in seamless joints, but in the stark, almost industrial geometry of shattered andesite blocks. Among the ruins are the famous H-blocks, so named for their distinctive recessed shape resembling a capital letter H. These are not simple building stones. They are components, each one an identical piece of a larger. Unknown assembly. The uniformity is startling, each H-block a near-perfect copy of the next, with crisp, 90-degree internal corners and flat, parallel faces. The stone itself, andesite, is a volcanic rock renowned for its toughness, a material that would quickly dull copper tools. Yet the surfaces show a smooth, almost polished finish, and the edges are sharp enough to cut a hand. Even more perplexing are the precise, cylindrical drill holes found in some stones, holes with consistent diameters and parallel sides that look as if they were made by a modern masonry bit. This is not the organic, interlocking puzzle of, it is the aesthetic of mass production, of parts designed to fit a template with machined exactness. The conventional narrative of hammer stones, copper chisels, and abrasive sand struggles to account for this specific combination of material, scale, and finish. The sharpness of the internal corners is particularly difficult to achieve with handheld tools, without chipping or rounding the edge. And the sheer number of identical units suggests a method of replication that goes beyond skilled craftsmanship into the realm of systematic manufacturing. This case study forces a difficult question. Have we, in our reconstructions, limited the ancient toolkit to only the items that have survived in the archaeological record? What if their mastery included techniques that left little to no physical trace? Some researchers point to the possibility of thermal shock methods, where a stone is heated intensely in a controlled area and then rapidly cooled, causing a thin layer to fall off, allowing for the precise removal of material. Others speculate about the use of plant-based chemical agents, acidic compounds derived from local flora that could have been used to soften the stone's surface for easier working, a form of natural etching. The most compelling possibility lies in specialized abrasives. We know they used sand, but what if they developed a proprietary abrasive paste, a mixture of a harder mineral powder like diamond dust or corundum, suspended in a binding agent and applied with precise, reusable templates? A copper tool coated in such a paste and drawn repeatedly along a guided groove could, with immense patience, cut the andesite with clean, sharp results. The drill holes could be made with a hollow reed or copper tube, using the same abrasive slurry and a bow drill apparatus, achieving that clean, cylindrical bore through relentless, guided rotation. Puma does not necessarily demand lost super technology, but it strongly suggests a lost technical recipe, a specific, optimized process for working this specific stone that was perfected by the culture, and then, perhaps, lost with their civilization's decline. The site stands as a stark reminder that our models are incomplete. We are looking at the end products of a sophisticated industrial culture, trying to reverse engineer the factory from a handful of scattered, flawless parts. The stones themselves are not asking for magic. They are asking for us to expand our imagination of what ancient ingenuity, when focused on a single, monumental problem, could truly devise. A flawless stone joint begins not with a chisel, but with a command. Behind every ton of perfectly fitted granite lay an invisible architecture of information, a logistical symphony conducted with nothing more than clay, string, and meticulous human memory. The 15th principle reveals that the true foundation of these monuments was not stone, but organization. Imagine the scale of the problem. A pyramid project might require 2 million blocks, each needing to be dressed, transported, and placed in a specific sequence over 20 years. This demanded a managerial precision every bit as sophisticated as the masonry. Without a flawlessly synchronized supply chain, the entire endeavor would collapse into chaos long before the first cornerstone was set. To coordinate this, ancient administrators developed the world's first large-scale project management systems. In Mesopotamia, they pressed cuneiform symbols into clay tablets, recording shipments of timber and rations for thousands of workers. Along the Nile, scribes filled papyrus scrolls with inventories, detailing which quarry team was responsible for which blocks, and tracking their journey by barge along the river. In the Andes, without a written language, the Inca used the quipu, a complex array of knotted strings where the position, color, and type of knot encoded vast amounts of data, likely including census figures. Tributary goods and construction schedules. These were not simple lists, they were dynamic databases. A foreman at a temple site could consult a quipu or a scroll to know that a shipment of 20 casing stones from the quarries was due by the next full moon, and that a work gang of 200 men from a specific village would be arriving to unload them. This administrative web ensured that the right material, the right tools, and the right labor were in the right place at the exact moment they were needed. It prevented bottlenecks at the docks, it avoided idle workers waiting for stones, and it guaranteed that the intricate sequence of construction, where each block depended on the one below it, proceeded without a catastrophic delay. This logistical genius transformed a monumental dream into a series of manageable, daily tasks. It broke down a generational project into a rhythm of seasons, lunar cycles, and annual flood patterns that dictated when materials could be moved. The project manager, perhaps a vizier or a high priest, had to think in multiple dimensions, balancing the slow pace of stone extraction with the urgent demand of the rising construction site, all while managing a temporary city of workers who needed food, water, and shelter. The precision of the final joint is therefore a testament to this invisible clockwork. A perfectly fitted stone is the end product of 1,000 earlier decisions, all correctly made and perfectly timed. It is the physical manifestation of information flowing as smoothly as the Nile, of commands remembered as faithfully as the knots in a string. The monument stands not only as a feat of engineering, but as a frozen moment of impeccable administration, proving that the greatest structures are built not just with hands, but with a brilliantly organized mind. Yet the very systems that preserved this knowledge also made it vulnerable. A master's understanding of stone was not stored in a library, but in his hands, his eyes, and the quiet rituals of the workshop. This living library could survive for centuries, but it could not survive the collapse of the world that sustained it. The decline began not with a single cataclysm, but with a slow, relentless shift in priorities. As great empires fragmented, the grand projects that demanded such exquisite precision simply ceased. There were no more pharaohs commissioning pyramids that were machines for the afterlife, no more god-kings ordering temples to align with solstice suns. The cultural engine that had fueled this obsessive pursuit of perfection sputtered and fell silent. Without a royal patron willing to fund decades of labor, the economic model for such craftsmanship evaporated. The long, costly apprenticeships, where a boy spent 10 years learning to listen to the ring of a chisel, became a luxury no society could afford. The guilds, those living repositories of technique, lost their funding and their purpose. Masters died without worthy successors, taking their unspoken secrets with them. New religious movements often accelerated this loss. In many regions, incoming faiths viewed the old stone gods and their temples not as marvels of engineering, but as monuments to a false idolatry. The spiritual imperative that had once demanded flawless joints was replaced by a mandate to dismantle or repurpose. The precise stonework was for new, simpler buildings, its sacred geometry broken down into mere rubble. The motivation to preserve the how vanished when the why was condemned. Simultaneously, new technologies offered compelling shortcuts. The Roman development of strong, hydraulic mortar and standardized brick was a revolution. Why spend a year grinding two granite faces to a perfect match when you could stack uniform bricks with a thick layer of binding agent in a fraction of the time? This was the dawn of a different paradigm, one that valued speed, scalability, and economic efficiency over the timeless, artisanal perfection of the seamless joint. Brick and mortar were democratic. They allowed for rapid fortification and urban expansion. The craft did not disappear overnight, but it retreated into niches, becoming a specialized art for royal tombs or cathedral foundations, rather than the backbone of an entire civilization's architecture. The most profound loss was the tacit knowledge, the deep, intuitive feel for the material that could never be fully captured in words. You could write down the proportions for a 3-4-5 triangle. You could describe how to build a ramp, but how do you document the exact pressure of a hammer strike that tells you a stone is about to fracture? How do you pass on the instinct for choosing the perfect quarry stone by the sound of the wind over its face? This knowledge was fractal, built from 10,000 minor corrections and sensory observations learned only through a lifetime of guided practice. When the chain of apprenticeship broke, that accumulated wisdom fragmented into folklore and half-remembered tricks. Later civilizations, even those with iron tools that were harder than the bronze of their predecessors, often looked upon the old walls with awe and bafflement. They possessed better metal, but they lacked the centuries of collective problem-solving, the refined recipes for abrasive slurries, the guild songs that encoded geometric rules, and the cultural patience that saw a year of polishing as a worthy investment. They could replicate the form, but they had lost the intimate conversation with the stone itself. The precision of the ancients thus became shrouded in legend, not because it was magical, but because the slow, silent school in which it was taught had finally closed its doors forever, leaving only its magnificent, unanswered homework scattered across the landscape. Our modern tools are finally learning to read the language of these ancient stones. For centuries, the precision of these monuments was a matter of awe and anecdote, something we could admire but not truly quantify. Now, a new class of silent observers is changing that, allowing us to reverse engineer the past with a clarity our eyes alone could never provide. Technologies like three-dimensional laser scanning and photogrammetry act as superhuman scribes, capturing every contour, every chip, every microscopic undulation on a stone surface. A scanner mounted on a tripod sweeps a monument with millions of laser points, building a digital twin so precise it can measure the deviation of a wall from true vertical down to a fraction of a millimeter. Photogrammetry uses hundreds of overlapping photographs to reconstruct a three-dimensional model, revealing tool marks and wear patterns invisible from any single vantage point. These are not just pictures, they are hyper-accurate data sets, letting us see the builder's handiwork in a way he himself never could. We can now trace the individual swing of a hammer stone across a granite face, or identify the specific abrasive grit used in the final polish by analyzing the microscopic grooves left behind. This digital archaeology confirms the legends with cold, hard numbers. Scans of the Great Pyramid's remaining casing stones show that their surfaces are flat to within a fraction of an inch over their entire length. And the corners approach a perfect 90 degrees, with an error margin that would be impressive in a modern machine shop. Ground-penetrating radar peers into the earth, mapping hidden chambers, foundation trenches, and even the ghostly outlines of long-vanished construction ramps, revealing the logistical skeleton of the site. Perhaps most humanizing of all, this technology is uncovering the mistakes. A scan might reveal a block that was slightly mise-cut, then expertly shimmed with a sliver of stone. It shows where a course was laid, then partially dismantled and realigned. We see the corrections, the on-the-fly problem-solving, the evidence that this was not magic but a process. It shows us the moment a master mason encountered an unexpected flaw in the material and devised a solution that has held for. This scientific lens does not diminish their achievement, it deepens our respect. We are no longer just staring at a perfect wall, we are witnessing the problem-solving journey that created it. The data provides the quantitative proof for the qualitative genius we have long sensed, transforming our wonder from a vague feeling into a detailed understanding. For the first time, we can measure the gap that a credit card cannot slip into, and in doing so, we begin to measure the immense, patient intelligence that made such a thing possible. That digital map of a perfect joint presents us with a profound and modern dilemma. Our tools now grant us the power to see with godlike clarity into the heart of ancient craftsmanship, but with that power comes an immense responsibility. For the first time, we can truly measure the genius of the past, but the very act of seeking that understanding can, ironically, place the objects of our study in jeopardy. This is the ethical tightrope of modern archaeology, a balance between the hunger to know and the duty to preserve. Every time a researcher drills a tiny core sample to analyze the composition of mortar, or brushes away centuries of soil to expose a pristine joint, a choice is made. We gain invaluable data, a chemical signature or a new photograph, but we also initiate a process of change, however slight. The monument leaves its sealed, timeless state and enters a new relationship with the modern world, one of light, air, and human curiosity. This forces a difficult question upon us. Should we ever attempt to physically replicate their methods on the original sites? The temptation is powerful to try and move a replica stone using their proposed techniques, to test a theory of rope and leverage on the very ramps that might have been used. Yet such experiments, even with the best intentions, risk catastrophic damage. The integrity of these places is non-renewable. A single misstep could erase the very evidence we seek to understand. The legacy is too fragile for trial and error. So how do we proceed? The answer lies in a principle of minimum intervention, guided by increasingly sophisticated non-invasive tools. The laser scanner and the ground-penetrating radar are revelations precisely because they ask questions without touching. They listen without speaking. They allow the monument to keep its secrets while still sharing their contours with us. This respectful distance is a form of humility, an acknowledgement that our role is not to master their techniques, but to comprehend their achievement. Our task as modern interpreters is therefore a delicate one. We are detectives who must not disturb the crime scene, translators who must not rewrite the original text. We must uncover the secrets of the past while honoring the silent, physical integrity of the works themselves. This means sometimes accepting that a perfect understanding may remain just out of reach, that some questions are meant to linger in the space between the stones. It means prioritizing the preservation of the monument's spirit and substance over the satisfaction of a definitive answer. When we choose to protect a weathered surface from further erosion rather than scrape it clean to reveal a hidden mark, we are making an ethical statement that the object's right to endure trumps our immediate desire to know. This perspective shifts our relationship from one of extraction to one of stewardship. We are not just studying history, we are now part of its continuity, tasked with ensuring these whispers from the past survive to inspire the generations that follow us. The true measure of our own civilization may not be in how well we decipher their blueprints, but in how wisely and gently we choose to listen. The echoes of their hammers are not just a sound from the past, they are a blueprint for our future. These ancient builders left behind more than monuments. They left in a different kind of intelligence, one that modern engineering and design are only now beginning to fully appreciate. Their first lesson is a profound respect for local materials, a cornerstone of sustainable design long before the term existed. They did not force a single, universal method onto every landscape, they listened to the stone. This principle of working with what the earth provides, rather than against it, drastically reduces the environmental cost of transportation and processing. A model of efficiency we are desperately trying to relearn in an age of global supply chains and carbon footprints. Their structures were inherently sustainable, not as a marketing slogan, but as the only logical way to build for eternity. Furthermore, their understanding of resilience, particularly seismic, was generations ahead of its time. The polygonal walls of the Andes were not just clever, they were a brilliant, preemptive response to earthquakes, using flexibility and friction to dissipate energy. Modern engineers studying base isolation and damping systems are, in essence, rediscovering the principles those ancient masons encoded in stone. Proving that sometimes the most advanced solution is also the most elegantly simple. They also mastered user-centric design on a fundamental level. By rooting their measurement system in the human body, the cubit, the palm, the digit, they created an architecture that felt intuitively scaled to the people who used it. This human-centric approach fostered a sense of connection and accessibility, a stark contrast to the sometimes alienating, impersonal scales of some modern construction. Even their process holds a powerful mirror to our own best practices. Their meticulous trial-and-error dry assembly, where stones were fitted and adjusted on the ground before final placement, is the ancient world's equivalent of rapid prototyping. It was a low-risk, high-feedback loop that ensured perfection before committing to an irreversible action, a principle at the very heart of modern design thinking and iterative development. Perhaps their most challenging lesson for us is one of perspective, the power of a long-term vision over short-term gain. They operated on a measured in generations, not quarterly reports. This liberated them to invest years in perfecting a single joint, because the project's value was measured in, not in immediate profit. In our world of planned obsolescence and fast-paced development, their commitment to permanence is a radical, almost philosophical, provocation. By studying their work, we are not just uncovering lost techniques, we are rediscovering a holistic, context-sensitive way of thinking. They saw the problem as a whole, the material, the environment, the human user, and the cosmic order, all woven together. Our modern world, for all its power, often suffers from extreme specialization, where the structural engineer, the materials scientist, and the architect may speak different languages. The ancient master builder was all of these at once, holding the entire system in his mind. Their legacy challenges us to look up from our computer screens and specialized silos, to remember that the greatest solutions often emerge not from a new technology, but from a deeper, more observant, and more patient conversation with the world as it already is. The seamless stones whisper of a skill so profound it can feel otherworldly. This very awe has, over time, given rise to captivating myths that seek to explain the unexplainable. Stories of lost high technology, of sonic devices that could soften rock, or even of guidance from beyond our world, have woven themselves into the narrative of these ancient sites. These ideas are undeniably compelling, offering a kind of magical shortcut that absolves us from the harder task of understanding. Yet in reaching for these extraordinary explanations, we risk overlooking the most extraordinary truth of all, the staggering capacity of unaided human ingenuity. These myths often stem from a very modern bias, a disbelief that such precision could be born from anything we would consider simple. We look at a 100-ton block fitted perfectly and think, our cranes could barely manage that. How could ropes and logs possibly suffice? This gap in our comprehension becomes a vacuum, and nature, as it is said, abhors a vacuum. Into that space flow tales of lasers and anti-gravity, not because the evidence points there, but because our own imagination of the past is limited. We project our own technological framework onto people who operated within an entirely different, but no less sophisticated, paradigm. The real disservice of these myths is not that they are imaginative, but that they quietly strip the ancient builders of their rightful credit. To say a pyramid was built by aliens or by a vanished supercivilization is to say that the people of that time and place were incapable of the work themselves. It dismisses the generations of observation, the incremental refinements, the cultural will, and the sheer, patient labor that archaeology continues to uncover. The evidence for a human, hands-on process is not lacking, it is overwhelming and consistent. We have the quarries with partially cut blocks still in, showing the wedge holes and fracture lines. We have the abandoned ramps, the worker settlements with their tools and ration records, and the experimental archaeology projects, where teams using reconstructed techniques have successfully moved and placed megalithic stones. This is the growing body of proof, a mosaic of practical, repeatable steps. When researchers like those at the Giza Plateau meticulously map the ancient harbor or analyze the wear patterns on a dolerite hammer, they are not finding traces of impossible machines. They are finding the sweat and strategy of a highly organized society. The choice before us is not between a boring truth and an exciting fiction. It is between a story that empowers humanity and one that disempowers it. The practical, incremental reality is far more inspiring, a testament to what communities can achieve when united by a common vision and armed with nothing but keen observation, shared knowledge, and relentless perseverance. Honoring that true achievement requires not a suspension of disbelief, but an application of critical thinking, a willingness to sit with the complexity and the scale of the human effort, and to find in that patient, collective triumph a legacy worthy of our deepest respect. The final and most essential tool was never made of stone or rope. It was forged from something far more intangible, the collective human spirit. We have explored the ingenious physics of ramps and levers, the sacred geometry of strings and shadows. But none of that technical brilliance would have mattered without a psychological environment capable of sustaining it for generations. The first pillar of this environment was a form of patience that feels almost alien to our modern sensibilities. In a world without quarterly reports or 5-year plans, the timeline for a great monument was measured in the of a king, or even across multiple reigns. A stonemason might begin his apprenticeship on a project he would never see completed, and he was okay with that. His contribution was not a task with a finish line, it was a stitch in a grand, eternal tapestry. This long-term perspective liberated the work from the tyranny of haste. A block could be ground for a year because the goal was not speed, but perfection that would outlast empires. This patience was not passive waiting, it was an active, focused endurance, a daily choice to prioritize quality over quickness. It was sustained by a second powerful force, deep personal and professional pride. For the master craftsman, his work was his signature. While his name might not be carved in the royal cartouche, his skill was permanently on display in every seamless joint, every flawlessly dressed surface. He wasn't just moving rock, he was contributing to something that would define his civilization for all time. The pride of seeing a block he had shaped with his own hands become part of the rising temple, knowing it would stand for, provided a profound, intrinsic motivation that no mere wage could match. His reputation, and that of his guild, was literally set in stone. This individual pride was 1,000-fold by the third element, a unifying collective purpose. Whether it was the Egyptian belief in a pharaoh's divine resurrection, the Inca's reverence for, or a city-state's desire to honor its patron deity, these projects were never just construction jobs. They were sacred missions, national endeavors that gave every participant, from the quarryman to the water carrier, a sense of belonging to a story larger than themselves. This shared cultural or religious imperative transformed exhausting labor into a form of pilgrimage or pious service. It fostered a powerful social cohesion, where the success of the whole depended on the meticulous care of each individual. This psychological trinity, patience, pride, and purpose, created the only mindset in which such precision could be born. It fostered an unwavering attention to detail, and a willingness to spend weeks on an adjustment invisible to anyone but the craftsman himself. Without this foundational spirit, the best techniques in the world would have faltered. The ropes would have snapped, the ramps would have been abandoned, and the stones would have been laid good enough. The ancient builders understood something we often forget, that the will to be precise is just as important as the skill to achieve it. Their monuments are not just feats of engineering. They are testaments to what human communities can accomplish when united by a vision that transcends the individual and embraces the eternal. The seamless joints of ancient stonework are a mirror held up to our own age. They ask us a quiet but persistent question: what does it truly mean to be advanced? For generations, we have measured progress in a straight line, from simple to complex, from primitive to sophisticated. We look at a stone hammer and call it crude, and at a computer chip and call it the peak of human achievement. But the silent testimony of these monuments suggests a different scale, one not of complexity, but of harmony, of durability, and of a deep, sustainable partnership with the world. Their technology was not a collection of gadgets, it was an ecosystem of knowledge, woven from the threads of astronomy, geology, geometry, and community. It was a system where the tool and the material, the builder and the belief, were all part of a single, coherent whole. They achieved what we often struggle to replicate: Structures built not for decades, but with a fraction of the energy expenditure, and without leaving a scar of industrial waste upon the planet. This forces a humbling realization. Perhaps progress is not merely about what we can make, but about what we choose to build, and how wisely we choose to build it. Their legacy is an invitation to broaden our definition of intelligence. It asks us to value the intelligence of the farmer who reads the soil, the carpenter who feels the grain of the wood, and the mason who listens to the song of the stone. Just as highly as we value the intelligence that writes code, it was this holistic, deeply attentive form of smart that raised the pyramids and locked the stones of. They remind us that the most profound solutions are often not about adding more, but about understanding more deeply what is already there. So the next time you see a photograph of a breathtaking ancient wall, or if you are ever fortunate enough to stand before one, try to see past the mystery. See the master observer reading the quarry, the surveyor capturing a stars rise in a line of string, the countless hands pulling in unison to a shared rhythm. And the patient craftsman, whose lifetime of feeling was poured into a single, perfect joint. See it not as a puzzle to be solved by outsiders, but as a masterpiece of insider knowledge, a brilliant, practical answer to the human desire for meaning and permanence. These stones are the ultimate artifacts of a different kind of genius, one that speaks not in the language of silicon, but in the timeless grammar of earth, sky, and human endeavor. If this journey from quarry to cornerstone has reshaped how you see the ancient world, consider subscribing for more explorations into the hidden logic of history. And down in the comments, I would love to hear from you. Which of these ancient techniques or principles did you find most astonishing? Was it the water level that defeated the curve of the earth, the 3-4-5 triangle that squared continents, or the profound patience that turned years of grinding into a seam thinner than a blade of grass? Your perspective is the next chapter in this ongoing conversation with the past.